7. So today we are moving on to chapter 8. I will try to do the part of the chapter 8 and then leave some time for your question at the end of the class. So chapter 8, we are going to introduce the sequential logic, which is important and different from the combinational logic we will learn. So combinational logic we learned in chapter 6 mainly. The combinational logic we know that it's going to run in parallel in our hardware. So for sequential logic, we talked about the difference between the VHDL parallel code and the C code or Python or even MATLAB code we run in a general PC. So those codes are intrinsically sequential. So one line after another. So you need to run those code in sequence. We can also do that in VHDL. So that is what we are going to talk about in chapter 8. So, and this is important because it will lead to our chapter 9 and chapter 10, when we talk about the counter design, the shift register design, and eventually we will learn how to design state machine, finite state machine. So they are all based on the sequential logic we are going to learn in chapter 8 this week. Okay, so what is a sequential logic? It is a digital circuit whose output depends not only on the present combination of input, but also on the history of the circuit. That means it will include the memory. So it remembers what the past state are. So what are the memory elements? So the memory element to remember the history of the circuit, there are two types. One is a latch, the other is a flip-flop. The difference is the condition under which the stored bit changes. So latch, we actually have the it's a level sensitive. So based on the enable signal or the input, we change the memory of the latch. For flip-flop, it's based on clock signal, the rising edge or the falling edge of the clock signal. We are going to look at the details about these two basic types of memory. So latch is a sequential circuit who has two input. So set and reset. There are two input to the latch. So when set is set to 1, the output will be 1. When reset is set to 1, the output will be 0. It's a very simple concept. So there are two outputs of the latch. So they are complementary output. We have Q and Q naught. So they are related. So output are always opposite. So this is the logic symbol and the timing diagram. With the input, we have S and R. S is the set input. R is the reset input. Output, we have Q and Q naught, complementary output. So they are always opposite to each other. Let's have a look at the timing diagram. When S, so at the beginning, both S and R are zero. So output remains the same. So let's assume the initial value of Q is 0. So it's complementary. Q naught is 1. When S is set to 1, the output Q will be set to 1. Correspondingly, Q naught will be the complementary of Q, that is 0. So after that, S will be changed back to 0, but the output won't change because the output only react on the change of input S and R. So when S is set to 1, output will be 1. But when S is changed back to 0, output will remain as its previous value. So whenever S and R, they are both 0, within this range, Q and Q naught remain the same, until R is set to 1. So at this time point, R is set to 1. So R is a reset input. So if R is 1, Q is reset to 0. Correspondingly, Q naught is reset to Q's complement. So that is 1. So when you are asked to work out a timing diagram, so to do it easily, you just simply figure out what's the Q's value first. Then the last step, you just convert Q, just do a complementary value of Q. So for this example, when R is 1, Q is reset to 0, then it will remain 0, regardless the change of Q of R now. So when R is changed back to 0, Q doesn't change. It remains 0 until the next time it sees the input S is set to 1. That will set the output Q to 1, and it will remain that value. So this is the concept of latch. Okay, so sequential circuit state, when set is 1, Q equals 1, Q naught equals 0. When reset is 1, Q equals 0, Q naught equals 1. That is the concept. Active high or low input. So what we just saw is the active high input. Both S and R, when they are 1, they are active high. When they are active high, we have the output change. So another situation is when we have the active low input. That is when we have an overbar to indicate the input are actually active low. The definition of the latch remains the same, but the active states are different. So in this example, we see S0 and so S0 and R0. The active states are low. So the inactive states, default states, are high. So when both of them are 1, the output doesn't change. When both of them are 1, the output doesn't change. When S0 is 0, that will set the output to 1. So when S0 is 0, Q out will be 1. Q out will be 1. When R0 is 0, Q will be reset to 0. So here is another example. So after Q is reset to 0, R0, this input, is changed back to 1 and then back to 0 again. This doesn't have any effect on the output because the output is already reset to 0. So R0 here can be bouncing around high and low many times, but it won't have any effect on the output. So this is the important feature of the latch. Later on, we will learn how do we use this effect in the circuit design, because it can be used on the push button debounce. So this is an application for it. Now we learn that this is a special feature of our latch gate. And remember that later on we will see how do we use it for real life function. The truth table for the NAND latch function is, we can see this NAND latch is the active low input. So when they are both zero, is forbidden. It's forbidden because both zero means we both set the output and reset the output. So that there is a competition. So which one is it going to be? So that shouldn't happen. So unless it's an error or it's a mistake. So this function is forbidden. When S naught is zero, that is set. That is set. So it sets the output to 1. When R naught is 0, it will reset the output to 0. When they are both 1, so the output will have no change. QT here, Q sub T here indicate that it's this previous time point value. This Q sub T plus 1 indicate it's a next time point. QT sub 1 means it's the T plus delta T. So it's the next moment after the input value changes. That's the NAND gate with active low input. Okay, so I mentioned that Q sub T and Q sub T plus 1 indicate the time delay of the output. For the NAND latch, we have these two possible stable state, that is set and reset. There is a feedback loop in the latch circuit to keep the stable condition. And let's have a look at that NOR latch function first before we look at the hardware circuit. So for the NOR latch function, it is similar to the NAND latch function. Apart from the input now, they are active high, S and R. So active high input. Again, when they're both 0, there will be no change to the output. When the reset is set to 1, the output will be 0. When the set is set to 1, the output will be 1. When they are both 1, the output is 0, but the function here is actually forbidden. You shouldn't have this condition. Okay, so this is the NOR latch function table and the NAND latch function table. So we can see these latch are formed by, this is formed by a NOR gate. And there is a feedback loop. So it's a pair of NOR gate. So because we have this feedback loop, it will create this memory to remember what is the previous state before the input state change. For the block diagram file for the NAND latch, we have the indicate input are labeled as NS, that's actually S over bar. NR is the R over bar, which we have already seen in the previous slides. Output are labeled Q and Q naught, that's Q over bar. In Cortex, so what Cortex is, if you read the textbook, is it will give you a lot of example in Cortex. Cortex is a software package used by a company called Altera. So who's Altera? So in the lab, in our lab, we are using Xilinx. And the tool, the software package provided by Xilinx is Vivado. It used to be another software package that is ISE. Now we are like upgrading to Vivado package. That is from the company called Xilinx. So Xilinx actually is the biggest FPGA company and FPGA design software provider. Probably not the design provider. I would say just the FPGA device provider, because there are companies like Mentor Graphics. So these are the other companies, they provide the design tools alone. They don't manufacture FPGA devices, but they provide very good design tools for the different FPGA hardware devices. And those tools are very advanced tools. They can give you a lot of optimization functions for generating very compact and fast synthesized and implementation result for your VHDL, from your VHDL code or even system C code. So we are not learning those in this class, but I have to mention those for you in case that you come up with those independent tools in the future. It's good that we learn the concept or learn the basics of the another tools here as well. So for Cortex, when we see examples in the textbooks and in the slides, they are general examples. So you when you see Cortex, don't think that this is for Cortex only, because these examples apply to both Cortex and Vivado, to both Altera and Xilinx FPGAs. Altera is the second biggest companies for FPGA as a FPGA manufacturer and provider. So if you basically, if you have the understanding of both, it will guarantee that in the future, whichever job you are going to get, whichever company that you are going to work for, we can cover about 95% of the market share. So you have a peace of mind that you will see what you will see in the future. You already know from the class, so from the contents we cover in this class. So it's either Altera or Xilinx. So Cortex is another software package. The VHDL design will be the same. The only difference is going to be the template. So when you have a look at the VHDL template for certain components, like we already know the like a decoder, multiplexer, counter, shift register, all of the concepts are going to be the same in terms of VHDL design. But the VHDL template for complicated components might be different. So those IPs might be different in different software. when you instantiate a component, the hierarchical design concept are going to be the same. So if you have that in mind, it will be easy no matter which software package you use in the future. Okay, so don't panic when you see the Cortex pop up in the next in the next few chapters, or when you read the textbook. It just happened that the textbook it used Altera and Cortex, but in the lab we practice with Xilinx and Vivado. So it's a good thing that you can get familiar with both concepts or both terminologies or names, but the design method that we learn in this class applies to both. So block diagram for NAND latch is the general block diagram that you will see. Even use Xilinx. So this is a block diagram generated by Altera tools. With the Vivado, you can generate a similar schematics, or something looks like exactly the same. Practical synthesis of NAND latch. So it talks about mainly the Cortex 2. We will I will just skip this. When you do your lab work, you will get hand-on exercise with the Vivado to implement latch and flip-flop. So equation, again, is going to be the same. No matter what tools you use, Cortex or Vivado, it's going to be the same equations for latch. And the circuit of this is going to be the same for both as well. Here we come up with the switch bounce. As I said, the latch has a very good functions in real life is a switch bounce, because it can just filter out all the sudden changes of the input. So the condition where the closure of a switch contact result in a mechanical bounce before the final contact is made. So if you connect your switch on your circuit or push button to a oscilloscope and capture the status changes triggered by your push action, you will see there will be a lot of up and down, and we will see the example timing example later with the timing diagram. So in logic circuit, switch bounce causes several pulses when a switch is closed, and it can cause the circuit to behave unpredictably. So how do we deal with this? We can use the latch to filter that out. So for the this is a push button. The ideal waveform is you have a very clean push down signal, give you a very stable and steady high signal to indicate this is a push down of the button. But in reality, it will be a lot of up and down, because when you push, so everybody is going to be different. So depends on how your so no matter how good you are at with the push down, so you probably, if you practice with a lot of computer game, the push down is hard and steady, sturdy. But if you use any physical, mechanical push button, it will intrinsically generate this up and down. So why do we not see this in most hardware? Because there are the switch debounce circuit. So this circuit will filter out all this bouncing up and down. This example, we use a NAND latch that switch with switch contacts connected to +5 volt. Bouncing is ignored since the condition results in input of the latch S0 equals 1 and R0 equals 1. So there is no change condition there. So this is the connection of the switch debounce circuit. So we added an no latch here. So we have the active low input to the latch. And this active low input to the latch actually are output of the push button. Let's have a look at the timing diagram. So for the S and R input, at the beginning there are, so S0 is 0, R0 is 1, so that generates a high output. So what state is this for the latch? So S0 is 0. S0, this is active low. That's why S0 is 0 indicates the set state for the latch, the set state. So that sets the output to 1. So the output Q is 1. Assume this is a push button. So when you are pushing the button down, S0 become 1, R0 become 0. But this push button is not stable at the beginning. It will bounce a few times before it settles down. So after this change of the state, the R0 become 0. So that is active low. Remember that is active low. So R0 becomes 0. That is a reset state. That will reset the output to 0. And after that, the reset state will be stable, because if you want to change it, you have to make sure that the set become enabled. But in this case, only the reset signal changes value, bounce up and down. So it won't affect the output value here. It won't affect output value. So that's due to the fact we have 2 input control. So we are not only use 1 input to indicate the output state. We are using set and reset, 2 input control. So that's why when this reset bounce up and down, the output won't be affected anymore once it gets reset to 0. Because at this point, it will only be changed once the set button is connected. So set signal is connected to, set signal is reset to 0, then that will set the output to 1 again. So hopefully this is easy to understand. And I believe you will come up to the push button debounce circuit design in your lab. So gated SR latch is a simple latch added with a gate. We will learn this in the previous chapters. So how do we design the enable gate or enable or inhibit gate? It's simple. We just add the AND gate to enable or disable signal. So this gated SR latch is we combine a latch design with AND gate to enable or inhibit the input. So this is a circuit. We have on the left side, we have the steering gate. So for both input S and R, we have to add the add one AND gate to it. So here we actually have a NAND gate to enable the input. On the right side, we have the latch. So this is what we call the gated SR latch. So for the gated signal, both S and R are enabled by this enable signal. So the whole circuit can be enabled by the additional enable input signal. So latch enable signal can be used as an on-off signal as what we did before. So on-off signal to let the signal pass or stop the signal. Or it can be used as a synchronizing signal. What does that mean? So what does that mean by synchronizing? Because in our circuit, we don't have to have only one latch. Let's say you have 32-bit or 16-bit or 8-bit. You want them to be enabled at the same time. So that's when we have the synchronizing signal to enable them at the same time to let the signal to pass through the input and be latched into the latch memory. So that is the fundamental of the memory design in the hardware. So we know that we have memory, RAM, ROM, read-only memory, read-write memory. So for the details, we are going to learn next semester for in the 387. I believe everybody here will be in 387 either next year or the year after next. So we will learn more details about the memory devices and memory control. But how do we build memory? So we build memory using latch and flip-flop. So this is the basic memory element we are learning right now. Okay, so gated SR latch function table. You can see for the first 4 rows, they are the same as the basic latch. They are exactly the same. The only additional signal is enable. So the last line here, it shows what does the enable signal do. When enable EN is 1, the latch function as normal. When enable signal is 0, so it doesn't matter what the input is, the output will be inhibited. So the output won't change no matter what the inputs are, it won't see. It is inhibited, but the output will remain the same. It will still remember the previous states. It will still remember the previous state. It won't change. It just won't change based on the input value. So that is inhibited. And it is actually different from the first line, the no change. The no change state is when the latch is enabled, both S and R, the input are 0. So this is a no change state. On the other hand, the inhibit state is when this memory is disabled, so it doesn't see the input change, but it still remains the previous memory. Okay, so gated D or transparent latch. This is the most popular latch and the simplest latch you can see. So it's transparent means the values on the input will be passed to the output. So a latch whose output follows is data input. When its enable input is active. When enable is inactive, the latch stores the data that was present when enable was last active. So basically it remains the previous memory values. So this is the circuit. It looks very similar to what we see before. The difference here is we have the D input, which is only one input now, and it passed through to this first NAND gate. Also, it passed through a NOT gate, and gets into the second NAND enable gate. So this is the circuit for D latch. So later on, we will see another memory, which is a D flip-flop, and it looks very similar to this one. Apart from the enable signal will become a clock input. Okay, so this is our gated D circuit. And the gated D function table, we have set and reset. When enable is 0, that is when the gated D latch is disabled. Doesn't matter what the input is, don't care the D, the output will remain the same. The comment here is store, means it stores the previous values. The function is no change, so it remains whatever value it is, 0 or 1, it doesn't change. So Qt equals Q sub t plus 1 equals Qt. So that is the disabled state. When it's enabled, it's transparent. So let's have the transparent state. So when it's enabled, when D is 0, output is 0. When D is 1, output is 1. So these two lines can be combined together. How? So that means when it's enabled, output equals D. Output equals to D. So you can read it from here. So output follows D's value. Output follows input. So output equals input, output Q sub t plus 1 equals D. So this is what it means by transparent. So gated D latch is very straightforward, very simple. D latches in Cortex 2, it will give us the HDL template for that. But in Xilinx Vivaldo, you also find the latch template, HDL template. You don't need to write it yourself. You just go to the template library and then copy paste the template for that. It looks, so the D latch symbol looks also similar. It looks similar within any software package. So with the input, enable signal, and output. Timing serial. So this looks very similar to our Vivaldo timing, so simulation. So within Vivaldo, we have a simulator, and when you do your simulation, it will generate the timing diagram. It looks similar to this one. Okay, VHDL process statement. We talked about process, and the process is sequential. So in this chapter, we will have a look at the example for writing VHDL process statement for the sequential circuit. So for D latch is so this example we here have a D enable signal as input defined as the bit. Q is an output bit. So the main architecture, the important part is a process. we say when we have a process, you have to have a bracket. And within that bracket, we call it is a sensitivity list. And it's a list of input signal. Why do we have to have that list? Because the process only runs when the signal listed in the sensitivity list change values. If they don't change values, the process will not run. So in another word, if you don't have anything list in the sensitivity list, will this process run or not? The answer is no. If you don't have a sensitivity list, if you have nothing in the bracket, your process will never run. But there is only one single exception. That is when you write a simulation code. So what is a simulation code? Is a test bench. You run it in a simulator. So when you do that, it will still run, but it will run in your software only. When you synthesize it, it won't synthesize. It won't run on your hardware. So this is a sensitivity list. So let's have a look at the values here. D and ENA. Those are the input signals we listed in the port. So as long as they change, this process will run because we now have them in the sensitivity list. It's sensitive. Okay, begin is the begin for the process. So this begin is a begin for the architecture, and this end is the end for the architecture. So this begin is a begin for the process, and this end process is the end of this process. So within the process, we have if-then statement. If ENA equals 1, enable equals 1, D get assigned to Q. Okay, so this is very simple. So you may say, oh, what happens when else? When else? So if ENA equals 1, then D get assigned to Q. So this statement imply, so it does this, but it doesn't show you that. It implies when ENA equals 0, the Q's value remains unchanged. So it will keep its previous value. So basically, if you want to complete this statement, you say, if this Q get assigned with D, else Q get assigned with Q. So Q's values will remain its previous value. So this is a HDL code. Okay, I think I will stop here today, and I will leave some time for to answer your questions.